This is Q1, Q2. Circuit will be reduced like this. This is all DC sources are there. If capacitor is there, capacitor should be shorted. And all constant current source are under this condition, we make this circuit. That tail current is constant, so we make this as open circuit. Okay? So there is no connection between this that tail resistor, the resistor. So the circuit will be like this. Now, in order to have this balanced dual input, we are considering dual input and balanced output. Configuration. So for this, first we will treat each of these transistor actions separately. Okay, first consider uh, only Q1 is active. Means we are considering only this signal, and we are considering this is off now. So we make that separately. We do all analysis separately. Then we use a superposition principle to club them together. Okay. So first consider Q1 is active, or we can say, or only P in 1 is applied. So under this condition, signal will be like you are applying signal here. Here the in, and this will be coming through this transistor. When it reaches here, it is common emitter amplifier. So in C1, we will get amplified inverted signal because it is common emitter. We will get output as inverted like this. So it is amplified and inverted at this C1 end. Okay. But this signal, which is reaching at IB, which will be equal to this IE, which will be coming through this and reaches at this emitter. So when it reaches this emitter, here base is common. This signal is off. So base is common. This transistor acts as common base amplifier. Okay. This signal that we are applying here will come through this emitter, and it will reach this emitter. and comes to this transistor in such a way that this configuration will become common base amplifier. This base is common to both input and output. So the input is now through this emitter, okay? And output is taken from this collector. So when it is in common base configuration, the output will not be having that phase shift, but the amplification will be. Amplification is same, but there will not be any phase shift. So whatever signal is will come here, but it is in the amplifier. So both of these should be having same magnitude. So in first transistor, this will act as, so Q1 act as common emitter configuration, common emitter amplifier under this condition, and Q2 act as common base amplifier. We are applying only V in one, so V in one will come here. From this common emitter configuration, we'll get output which is inverted and amplified, and that signal comes here to the second transistor, and the input is given like it is passing through this emitter. Base is common, so this will act as common base amplifier, and output will be amplified, but which will be in the same phase. There is no phase shift in common base amplifier. So that's first condition, and we have to measure the output voltage in such a way that what is the output at C2 with respect to C1. This balanced output. So C2 with respect to C1 we have to measure. So if you are having input like this, okay, so this is your input. Output you have to measure like this. Here you have same phase with amplification, some amplification factor. Here you are having different phase that is opposite to that of original signal, 180-degree of phase. So the total will be, output will be whatever potential at C2, so C2 with respect to C1. This is your output. Okay. So now if you see here you are having positive potential. Let's say this is 0. Say this is, for example, 5. Okay, positive 5. And this is negative 5. Okay. And here we will be having positive 5 here and negative 5 here, which is out of phase. So when you take the difference C2 with respect to C1, what else voltage you take? So suppose I am taking the voltage at this point. So this is 5. 5 minus 5 will come. I'm taking this point. These 2 points. Consider. So here I am having 5, positive 5, minus potential at here. That is minus 5. So total potential will become 10. Right? So the output will become this with here I will be having minus 10. C2 with respect to C1. That's what we have to measure. Right? And in the second case, so this is only one input we are considering with the balanced output. Okay. Now we consider the second input, same scenario will happen. So for second case, consider only I should not write this. We consider only one input is active. Consider only V in one is active because Q2 is also active at that time. Okay. Like that. Consider only V in 2 is applied. Second case. And in that case, same scenario, only that so here we are applying that signal now. So applying signal, same signal here. What will happen? C2 in C2 will be getting that out of phase signal because this Q2 will act as common emitter configuration now. And that signal will be coupled to this emitter from this emitter. That's why it is called as emitter coupled amplifier. So this signal will be coupled through this emitter to this one, this second transistor emitter. Okay, so that will be coming through here. So this Q1 will act as common base amplifier now, and this output will be having same phase with some amplification, same amplification. Okay. Here now this is in phase, this is out of phase. Now you have to measure, say, in the same way, what will be that potential when Q2 is active. So this is, it means when the second input is active. So this is for input 1, and for input 2, what change we can expect? This is minus 5, this 5. I'm just taking as an example 5. This minus 5, this 5. Now this is minus 5. Minus 5, I have to take C2 with respect to C1. So minus 5 minus 5 will come here. So total will become minus 10. Right? Minus 5 minus 5. Here it is minus 5. Here it is plus 5. So minus 5 plus minus 5. Sorry, plus minus 5. Minus 5 will come. Total is then total will become minus 10 initially. Right? So for this case, the first cycle it will come minus. So here this is minus 10. In this time, the difference is from with respect to C2, what we have to measure. So that will be minus 5 minus that second is 5. This will give you minus 10. So that I have total potential. So the difference or the potential across C2 and C1, that will be minus 10 initially, then it will go to the positive cycle like that. So the total output, we are giving input like this here, but we are getting total output which is out of phase to the input signal. So I can call this terminal as inverting terminal. Or inverting input. Okay, because when I apply input here, my total potential is out of phase, which is coming inverted. But when I apply signal, this arm, this is coming like this, total output is coming like this. So this is non-inverting because it is in the same phase of the input signal. This is non-inverting. This you can observe in op amp also, because this is the circuit, first stage circuit of that op amp. So you will be having that inverting and non-inverting. Okay. So what will be that total output? So this is for first input, only one input is active. This is for second input is active. If both are active, then we are measuring C1 and C2 across that C1 and C2. Then the difference that you have to take, then that will be the difference between these two. Okay, C1 and C2. So this time, if we consider that V0, I will call this as V01, V01, this is V02, V02, okay, because this is for only that input 2 is active, this is for that input 1 is active. I will take this as output when input 1 is active. This V02 means output when only that input 2 is active. So total output will be V01 plus V02 by using that superposition principle. Check there is space or not. So by using superposition principle, V0 will be equal to V01 plus V02. Okay. So what is V01? V01 is A times VI1, and V02 is A times uh, VI2, right? But VI2 is out of phase, or you can say this term is out of phase as compared to this one. They are coming out of phase. One is coming positive, and the other one is out of phase. So I can take total output V0, which is equal to A times either one of these we can take minus. So A times VI1 minus A times VI2, and that will give A times VI1 minus VI2. And this I can further write. Huh? Huh. We are considering both transistors as identical. So this will become VID, where VID is VI1 minus VI2. So basically, this in this configuration, the difference between the two input signal is getting amplified. Okay, the output. So the difference between two input signal is amplified. That's what this means. We are applying V in 1 and V in 2. You can write it as V in 1 and V in 2 here also. Just put it as by VI1. So the difference between those input signal is amplified with an amplification factor of A. That is what we are getting output. That's why it's called as differential amplifier. Whatever we are giving on those terminals, VI1 and VI2, the difference between those two signals is which is getting amplified at the output. Okay. So here the gain of this, if you consider the first case, for example, in this case, gain will be RC by 2 RE dash, we just there in the last class, which is corresponds to that single common emitter amplifier. Okay, actually it will come as A equal to RC by RE plus RE dash. Then there will be one more RE dash from the second transistor, and this RE is not there. Emitter resistor we are not connected. So total dynamic resistor will become RE dash plus RE dash because of the second transistor. So the total gain will become RC by 2 RE dash. And this is for first common emitter amplifier configuration. Okay. Same will be there for second configuration, right? When we consider the second input, there also will be having same gain factor. So the total gain will be again 2 times of this, or 1 by 2 times of this, right? So total gain will become RC. This will become RC by R. RC by R. Total gain will become increased when we have both inputs. Okay. So that's about the gain. Then we have to look at the input impedance. Input impedance. So this input impedance for the case of common emitter configuration. So this, that will come as 2 times beta RE dash. This is for both cases. In one case, it will come RE dash only. So if you consider both, then it will become 2 beta RE dash. So for a single common emitter configuration, if you consider that input impedance Zi, that will be coming like beta times RE plus RE dash. Okay. Now this RE is replaced with the second common emitter dynamic resistor, second transistor's dynamic resistor. So this will become here this will become RE dash. So 2 times of RE dash times beta will be the total input impedance. Okay. So this is from conventional common emitter amplifier. The input impedance will be like this. There we have instead of this we have RE plus RE dash, not RE dash. But in our case, RE is not there. Instead of that, we have the dynamic resistor of the second transistor. So that will come here. So total will become RE dash plus RE dash. Then it will become 2 RE dash times beta. That is the input impedance. So this beta is coming in 100 to 1000 of range. Okay, that current gain, and then this will this RE dash dynamic resistor, that will come somewhere 25 milliwatt by IB. This is in the emitter resistance. So IE, so this will be in milliampere. This current will be in milliampere. So this also approximately you will get temperature 3 times of some value because this is in milliampere. So this will be in the order of 10 raised to 3, that RE dash dynamic resistor. So total beta times RE dash, that is this times some temperature 3. So this will almost comes in range of some 100 kilo ohm to mega ohm. Okay, total input impedance correspond to one single common emitter configuration will come like Z equal to beta times capital RE plus RE dash. So RE is not there. RE dash will come from the second transistor. So 2 RE dash times beta will be the input impedance. And beta can be having value from 100 to 1000 range. Okay. And this RE dash will be having value in the order of 10 raised to 3 ohm. Okay. So if you take the product of between these two, then it will come in the 10 raised to 6 ohm. Okay, so that will vary from 100 kilo ohm to 1 mega ohm. So in mega ohm. So input impedance of this differential amplifier is very high. From this input impedance of differential amplifier, I mean emitter coupled differential amplifier, is very high because it is coming in mega. Now, what will be that output impedance? So output impedance will be nothing but ZO equal to RC because we are taking that output from collector and the only resistance we have is that collector resistance. So the output resistance will be only that collector resistance. So output impedance is nothing but RC. Okay. Now we'll look to the other configurations that are not that much important, but just cover that. Okay, and I will just discuss what will happen to the other configurations. So the second case we are having two inputs, dual inputs. Second one, dual input and unbalanced output. I'm not going to explain these things. Not that much difficult. Once you understand that first one, then it is not. This resistor will be there. We are applying both inputs. But we are taking only this output, like C2. Considering only C2, this is grounded. We are not considering this terminal. Okay. So we are considering this C2. This is not actually grounded, but we are taking this C2 with respect to ground. Output will be taken from C2 with respect to ground instead of C2 from C1. So only one output terminal is there. That's why it is called as unbalanced output. Dual inputs are there. So all scenarios will be the same. Gain will be equal to RC by 2 RE dash instead of RE dash because half of the first one will come because only one terminal we are considering. Okay. Initially we have taken, for example, in the first case we have taken like this one 10 and the next one will come like this. This is minus 10. Okay. This we have taken that gain I'm saying this we have taken. So the total gain will be doubled. It will be much high. You consider that gain. But when you consider this case, we are taking only this one. First case only or the second case. So only one output we are considering. So the total gain will be half of the first one. So total gain will become RC by 2 RH. Okay. And second one here is that in this case, we will be having that DC also. I mean, in a real circuit, I'm not considering about AC analysis. When we consider both DC and AC, when you have that real circuit, in the previous case, we are having DC component here and DC component this part also. And when we take that difference, that DC components will be cancelled. But in this case, we are having DC component only this side. We are not taking any differences of the DC component. So DC component also will exist. Okay? When we consider the real circuit, I'm not talking about AC analysis. When we consider the real circuit, in the first case, we will be having DC component to this output. So this DC component will be shared. This is voltage divider. So this is shared with this collector also. So this DC will be here as well as here. So when we take the difference between that, that DC component will be gone because same DC is applied in both. So if 5-volt DC is applied here, 5 volt is in here also. When we take that difference in the first case, that DC component will become matched. Okay, but in this case, we are considering only this side, taking output from this side with the ground. So this DC component exists. So in this case, both AC and DC are present. Both AC and DC components are present. Okay. And here input impedance will not change. Input impedance will not change. Okay, and first one we have already taken. Output is taken. It is taken from E2 with respect to ground. So these are the important points in this your inputs and imbalance output. Now, if we consider third one, which is single input and balanced output. This means that we are applying only one signal, one input, and we are taking the output from C2 with respect to C1. So the circuit will be we are applying only one signal. Here. This is grounded. So the output is taken from C2 with respect to C1. Either way you can connect this one. You can give your signal in the inverting terminal or in the non-inverting terminal. Okay. So in this case, what will happen? You are applying signal here. You are applying signal here. Okay. And you will be getting that amplified signal with 180-degree out of phase at this C1. And the same signal will be gone through this, and in this terminal, C2 will be getting without any phase. Okay. The first case of that dual input and unbalanced output. Okay. Same scenario. So the output will be from this to C2 with respect to C1. We have to take when both collectors are there. Both output we are considering balanced output. So in that case, we have to take C2 with respect to C1. So that will come. C2 is in positive here. Here it is negative. Okay. So of course this is 5 and this is minus 5. 5 minus minus 5 will become 10. Right? So the total output will be like this. So this will become 10. Okay. Now you can apply the same signal here also. When you apply this signal in this terminal, you will get it in inverted, amplified but inverted. And gain will be V0 equal to A times Vi, and where A will become RC by RE dash. You apply only one signal and taking dual out. So if you are giving in non-inverting terminal, it will come the opposite. Only that is the change. And the fourth one is single input and single output. Okay. So in this case, this is nothing but a simple common emitter amplifier. So no advantage. I would say no advantage over common emitter amplifier. So not used. So this configuration we will not use because single input, single output means it is simply common emitter amplifier. Okay, which means that we are only considering this part of the circuit or this part of the circuit. Either way, it will act as a single common emitter amplifier. We are taking this with respect to ground. So it is a conventional common emitter amplifier. So there is no advantage of using this particular configuration because we can directly take one single common emitter amplifier instead of using this coupled. So this configuration is not used because it is simply a common emitter amplifier. So instead of that, we can just use any common emitter amplifier instead of this